system from the 1990s. And they have been enhanced and enriched over the years to be a very powerful set of tools that are used for debugging, controlling debugging, and analyzing applications in a real-time environment. So they are proprietary to Concurrent, and they are licensed by our company. Briefly, just to say about licensing is that unlike other vendors that have products that once the nightstar tools are licensed, those are licensed in perpetuity. So once you have a license for the nightstar tools, you don't have to write a check to Concurrent every January to make sure the tools continue to operate. So I'm going to briefly give you an overview of what the 5 different tools are, and then I'm going to go into a demo and walk you through. So it's a simple, contrived, so to speak, demo, but to illustrate different features of the tools as they apply with each other. So NightSim is a scheduling utility. It's a graphical interface tool that actually interfaces to a subsystem of the Red Hawk Linux kernel. And so it allows one through a user command line or through a graphical user interface to allow the kernel to schedule processes and threads on different CPU cores at different priorities. So your application itself is not require any internal timing mechanisms. So the scheduling of processes and threads can be done externally to the processes and threads, and it essentially works down to about 10 kilohertz frame rate. I don't know what your application, what your frame rate may be, but that's what the NightSim tool and the frequency-based scheduler will provide. If you notice in the lower right-hand corner of this graphic here, I just try to illustrate that this tool, they work in a client-server environment as well, and I will be illustrating some of this today with the other tools. Another utility we have is called NightTune, and this is, I would say, this is the least complex of all the nightstar tools. Would be geared more toward a operator, and as opposed to a actually development engineer, software programmer, although it's applicable through the entire range. But the NightTune utility essentially allows one to acquire information about the performance of the system and then have control over how the processes and threads are running on the system itself. So it sort of gives you the 50,000-foot flyover on how the system is operating. And again, I will be showing you some of the features of this particular utility shortly. The next utility here called NightView. This is a source code debugger that Concurrent has developed over time. If you have used GDB in the past, you would find that NightView is very much GDB-like. However, it has no GDB code in it. It is completely written by Concurrent. One of the things about the NightView debugger is that, as opposed to the debugger having supervisory control of how the processes and threads are under debug, NightView goes about and actually hot patches into the executable code itself, so it allows processes and threads to run at real-time speeds, and allows and facilitates and has minimal impact on debugging real-time applications. The other utility in conjunction with Night View is our Night Probe. And essentially what this utility allows us to do is to attach to shared memory regions, either POSIX or System 5, process address space, and also to PCI devices. And it is non-intrusive acquisition of variables that have been declared static or global within the process. So it allows one to look at process data on the fly, independently of the execution of the process. And also, because the way it works, it also allows you to poke. So you can go in and modify variables in a process externally to it by using Night Probe to attach to the process. Again, it's something I will show you a little bit about what Night Probe can do for you during this demo. And finally, the last utility here called Night Trace. This is the Night Trace utility is, I would say, it's probably the pinnacle of all of the nightstar tools, in that it allows one to analyze the performance of the system as it's running. And not only, when I say the system, not only is it's the kernel, but also user application code itself. And it is supported by the Red Hawk Linux kernel with various functions that have been implemented into the kernel itself, that if tracing is enabled and active, the kernel will generate trace events into an address space reserved for that, along with timestamp information and other auxiliary data. And then the graphical utility allows one to acquire those trace events from that shared memory region, and then visually display it in graphical format, similar to one might see with an oscilloscope. And the resolution of the timestamping is down sub-microsecond, and you can see the events occurring, interrupts being switched in and switched out, system calls, exceptions, processes being switched in and out of the system, and then of course the actual kernel events from itself. Now that is quite interesting in itself, that allows one to see what's running on which CPU and what the different processes and threads are performing on the system. But to get even finer detailed and finer granularity within an application that is compute bound, when a process is switched in, the kernel only knows that the process is executing and has no further information about what that process is doing as while it's being compute bound there. So we have an API that goes along with the Night Trace utility that allows one to place additional trace events into user applications while it's running, and then to get more detailed information what's going on in the execution of the process or thread. So these are the 5 nightstar tools, and today I'm going to actually be talking about all but the NightSim tool. I can do at another future point in time, we could talk about NightSim if that is of interest to you. Are there any questions?
Just one question, 2 questions actually. One is, you mentioned the license is perpetual, so does that still imply that all upgrades and supports will still be available?
No, sir. If you carry maintenance, if you have a maintenance contract, then yes, of course, you can get upgrades to Red Hawk Linux and the Nightstar tools and that if you have a maintenance contract. But if you, for example, if you have you acquire a system from us and perhaps you use it for a couple years and you have maintenance on it, and then you don't need maintenance anymore, the tools will continue to function for the life of the system. But once maintenance has elapsed, then you're basically frozen at whatever release that you were at that time.
Understood. Yep, absolutely. So, okay, there's a maintenance contract. Makes sense.
Yes.
Um, and so, regarding the tool sets, are these, I assume, like some of these tool set can be run along with the, like, so if our vehicle is in water, we can develop tools basically to attach to that run at runtime, right? Or this is only a benchtop kind of tool set?
Well, they are, if you have an interface that you can communicate with
Mhm.
the device um, as it's running, yes, of course, they are all client server based.
Okay.
And then so on your desktop, for example, you might be running the tools, and then you would tell the tool to attach to that device wherever it may be
Mhm.
across the network, and then you can do that remotely.
I see. Okay.
I'm not really familiar with your actual application. I understand that you're doing some kind of underwater vehicle. Um,
Right.
I assume you're either going to have an umbilical attached to it, uh,
No, we don't have anything attached to it.
nothing to it. Do you have a communications interface to it?
Not once the vehicle is in the water. Once it dives, there's no interface. Basically, it's on its
Yeah.
own.
Well, you can once you could well the night trace utility could be configured, the trace kernel daemons to be configured that perhaps after the control software, after the vehicle dives, perhaps after 2 or 3 minutes, it starts doing kernel tracing
Mm.
to collect some information and records it into a file system somewhere. And then when you recover the vehicle, you could recover that file and then do post-mortem analysis.
Okay, hey, that's exactly what I was thinking. All right,
Oh,
cool.
okay. Yeah, that's totally possible. Yes.
Awesome.
So, okay.
Um,
So
mhm.
I'm going to start off here and show you a little bit about the nightstar tools. The first one I'm going to show you here is Nighttune, and let's see. Well, that's not what I expected here. Just a second here. Um,
While you do that, quick question: since the session is being recorded, will we get a copy of the session recording?
uh, you'll have to talk to Bill about that.
Yeah,
I think.
I don't, I'm fine with it.
Yeah.
Great. I think it'll be great for some other folks in our team to review what you're presenting here. I think it'll be valuable for them to see it. Thank you.
You're welcome. File. Okay, well, this is the first bump. I had a different, this is what you're looking at on this screen here is the default configuration file for when you start up Nighttune. This is the factory default. I actually had created another default, and um, for one reason or another, I have misplaced it. But anyways, what we have here um, on the left-hand side is what's known as the process list, and allows the user to see exactly what processes and threads are running on the system at any point in time. And not only is it single process, but also multi-threaded processes. For example, even Nighttune itself is a multi-threaded process where you can see the actual threads that are running of the Nighttune utility on the system. But that, as far as that goes, that is somewhat of interest because I'll show you how you can move processes and threads around on the system in a bit. But over on the upper right-hand side is our screen here where it illustrates shielding and binding of the system. And this is a feature unique to Red Hawk, or somewhat unique to Red Hawk, where that one has the ability to have some level of control of how the hardware functions. And that is essentially how we get real-time or well, not only just that, but as far as user goes, how you get real-time performance on the system is because one has the ability to set aside CPU resources for real-time applications and then target those resources toward those particular CPU cores. So you can see that this is essentially a very idle machine right now, and on the bottom side here is a bar graph that illustrates that the CPU is essentially quiescent. So what I'm going to do here on this particular system, just to illustrate a few things about this, I'm going to go to root and go to the top level directory of the kernel source tree. Not part of the demo here, but you should be aware that when you get Red Hawk, you get the source code to the kernel. And so I'm going to start a kernel compile just to illustrate the activity on the system. So as you can see, over on the right-hand side, all these CPU cores have essentially gone near 100% utilization. And in the lower right-hand side, you can see the bar graph where you're spending a majority of the time in user space, and there's some in the kernel space in IRQ processing and so forth. Now, one of the things about the way the Red Hawk kernel has been developed and supported is I have the ability to go in here and tell that I want to change the shielding of how the system is functioning. So here I'm going to tell the Nighttune to shield off CPU core number 3. And what that will do, it will prevent CPU core 3 from servicing interrupts, servicing the local timer daemon, or servicing any processes. And once I hit apply here, the CPU core 3 is now shielded, and any process that has been on CPU core 3 will be migrated off to the remaining cores on the system. So what I've essentially done here is I've taken a 4-core processor and I've turned it into 3 cores that are running standard processes, and I have reserved core number 3 for perhaps an application that I want to run in real time. Now, not only can we do this once I have a process shielded, I could then quite easily go down here to, I'm just going to pick a process here just for illustrative purposes. And I'm going to pick the bash shell here. You can see that the bash shell here on this system says it's running on CPU core 1 right now, and it's allowed to run on any of the CPU cores. But because CPU core 3 is shielded, it will not run on CPU core 3. I could tell Nighttune now that I want this particular process to only run on CPU core 3, and I hit apply and close, and we can now see that that bash shell is now bound to CPU core 3. Well, that is its shielding, but however, it is not actually. It's been blocked. It hasn't actually tried to run. But the next time this bash shell attempts to run, you'll see that it has now been migrated to CPU core 3. So this is a nice utility about working with the Nighttune, is that you can do a lot of this stuff dynamically and experiment on how the your simulation may function. during your development phase. Are there any questions?
No, no questions. That's pretty cool. I'll just say that. Pretty easy to do that.
So I'm going to go back and tell it to apply that. And now it's no longer bound to CPU core 3. And now if next time I hit return, you can see that it got migrated all the way from CPU core 3, and now it's running on CPU core 0. So this is all done dynamically and totally, behind the scenes, so you don't have to be concerned about whether if I did this at the right place or time or whatever, that the kernel handles all this for you. Now, also with, I'm going to add a page here. On the system, as you know, the devices out there that you have on the PCI bus, they also generate interrupts, and they can impact the performance of a real-time application. So you can see on this case on the left-hand side, these are the various interrupt levels that are being enabled on the system, and that this gives me essentially how many interrupts per second are occurring on the CPU cores at this time. And just to note that Ethernet 0, there is nothing occurring on CPU core 3 because I have CPU core 3 shielded. And that the local timer interrupt is also, there's no interrupts occurring on CPU core 3 from local timer, to the local timer daemon. That does not mean that you cannot target interrupts to a particular CPU. So if you, for example, were using some particular device, and I'm just going to pick something here just for illustrative purposes. In this case, I'm going to pick the real-time clock and interrupt module. This is we're not really using it for this demo, but if I wanted to force interrupt number 135 to be serviced by a particular CPU core, I can go in here and I'm going to clear all, and then I'm going to force that interrupt to be only serviced by CPU core 3. Now, in this case, again, the arson card is not generating interrupts, but that little visualization here is actually supposed to be a piece of chain to indicate that the interrupt, the arson interrupt, is now bound to CPU core number 3. So you have a lot of flexibility and control over the system. Now, you may have some particular device or a sensor in your vehicle that you want to that needs to communicate or generates interrupts back to your application, and then you could have, for example, I assume you're using 4 or more cores on your system, that you may have your real-time application may needs the, let's say it's an 8-core processor. You shield off cores 4 through 7 for your application, where it's a multi-threaded application, and the threads run on cores 4, 5, 6, and 7. And perhaps the thread that's running on core number 6 is the one that's being driven by some interrupt coming in from one of your hardware devices. You could then force that interrupt to be serviced by CPU core number 6, which in turn drives the application or the thread that's running on CPU core number 6. So there's a lot of potential here with the NightTune tool to set this all up for you ahead of time. Okay, so that is a little bit about NightTune, and I'm going to now let's clear the that binding of the interrupt. And I'm going to go back here to the first page, and I'm going to reset the shielding for now. So CPU Core 3 now is available for anything you want to run. Okay. So the night tune is, again, really nice for ad hoc experiments and to see what's going on in the system. Now, there's a lot of other things that night tune can do that we can look at. You know, besides CPU usage, you can look at physical memory, your disk devices, interrupt processing, network activity, disk activity, and kernel activity and CUDA activity if you have CUDA, and so forth. But it's a great tool for gathering general purpose information about the execution of your application while it's running. So the next tool we're going to take a look at here is Night Tune. Night View, rather. And here I'm just to let you know, here in the this demonstration, I am in the sitting in our training room right now using my laptop to do the demo here. It's running Red Hawk Linux, and I have an iHawk computer, a 4-core iHawk computer, in a remote location that I'm going to do remote debugging with it. So here I'm going to start up Night View, which is our debugger. I'm going to tell it, I'm going to target a computer on the network called Mini-X that happens to be located in my office. And I'm going to tell Night View that I want to run a program that I want to bind it to CPU Core 3 and it's in my home directory under a subdirectory called tutorial, and it's called app. This is a sample code that we ship with Nightstar tools that has a lot of things built into it that makes it nice to do a demo with as well. So what I've done now is I've started up the graphical user interface locally, and I have started up a process on the remote computer that activates this app program, and it has now populated locally the source code here of the executable for debug. And just to also say that you, with the under Red Hawk, you do not have to link applications to anything other than to link it. We have no special libraries for doing debugging. We use the standard stuff. All you have to do is compile with the -G switch, so you have symbols, so we can do symbolic debugging. So this is our Night View debugger. Now, so here with the debugger, I want to say a few things about it. First of all, we have what is a debugger? It allows you to monitor and control the execution of a program. So you can look at memory, and then you can have some control over it. Well, under Night View, as you can see here, I have activated a program, but it's not actually running yet. I'm going to go ahead and resume it. And now that I have it resumed, you can see that I have the threads. Well, this particular application creates 4 threads, and the threads actually compute the sine and cosine, and there's another thread for doing heap debugging as an example. And there's a watchdog thread that needs to run all the time because it's well, it's a watchdog. And if it for some reason, if it stops running, it will cause an overrun condition. And I can show you that if I just put a breakpoint in here, let's say line, I'm just going to go up here like line 52, for example, and place a breakpoint in there. You can see that I'm going to disable the breakpoint and then resume it. That the deadline was missed by a number of seconds because the watchdog thread also stopped when the sign thread hit the breakpoint. Now, oftentimes you'll have these real-time applications where you need to have thread control. So with Night View, we can then protect a thread from breakpoints. So now the watchdog thread is protected. So now if I go back and re-enable this breakpoint and resume the process, you can see that I have hit the breakpoint. But down here you can see that the watchdog thread has been protected and it continues to run. So that's a very powerful thing under Night View, that you have this ability to protect threads from breakpoints that may be occurring in other threads. Now, in addition to a breakpoint that everybody is used to with a debugger, Night View also supports a number of other event points besides that, and I'll briefly talk about that. This is setting a breakpoint up here graphically. This allows you to do a patch point, and we'll take a look at that this morning. This is where you can actually patch in code into the running application dynamically. You can monitor events or monitor variables while they're running. You can set trace events into the running application, and then you can set things up for heat points, and you can for system watch points, and system calls are also available to you. So you have a lot of ways of looking at and controlling the execution of a program. So we're going to create a monitor point here down here at line 52, and for example, in the sign thread here, when I'm running, and so because we're running right now and the sign thread is running, if I can't, the only way to look at this variable is with the process stopped. So if it's stopped, I could then go in there and actually look at what this happens to be. But let's see, data, and there is the count. But once I'm running, you can't really see that. But under Night View, we can actually go in here and we actually can add what's known as a monitor point. So at line 52, I'm going to tell it that I want to look at data count, and we'll call it data count. And I'm going to look at, in addition to that, we're going to look at data value and give it a label too. Hit OK. And now we can see what this has actually done is while this program is running, I have patched into the binary. It's essentially is compiled into executable code and then patched in there that we can now monitor these variables that you typically can't look at unless the process is stopped, because when it's running, it's on the heap somewhere or on the stack. So this is one way of looking at data live while the debugger is running and the process is under debug. Are there any questions?
Not from me. I'm good. This is neat.
Okay, so another thing about again, controlling the execution of a process while it's running. I'm going to show you another thing we can do. We can go in, can patch in here, and let's just assume that this expression here was incorrect. It's going to increment it by this delta value. So this is it. So I'm going to tell it. I'm going to branch to line 54. And you can see that once I branch to line 54, the data value has ceased or stopped incrementing. I can disable that patch point, and we can see that it now is it's cycling between plus and minus 1. And when that patch point is active, I've actually skipped over this expression on line 53. And down here at line 54, I could then go in here and place a patch point in here. And I'm going to now say that data angle is minus equal data delta. Now, of course, I could have changed it to anything. Any valid expression could have been patched in there, but you can notice here that, in fact, that by having this patched code in here, I'm now changing the value of here of data value, even though that I've skipped over it at line 53. So let me take these out and return everything back to its normal state. So these are things we can do with Night View to monitor and control the execution of processes and threads. Okay, moving on with the next utility here on the system is Night Probe. And in this case, I'm going to start up Night Probe. I'm going to target that other system. And in this case, I'm going to tell Night Probe to attach to a program that I'm running, the same one. And Night Probe then locates that process and attaches to it and allows me now to look at process data on the fly as the process is running. So let me just go change this to the format to real and change that format to real. So while one thread is computing the sine of an angle, the other thread is computing the cosine. They're essentially inverse of each other. Now, another thing about the way this Night Probe, as I said, allows us to have control over the execution of a program. If we go back to Night View, the debugger, and look down at line number 107 here, the main thread is controlling the execution of the other threads through this check on whether the value of state is either in a hold or run condition. And so as long as the variable state is set to run, the threads will be allowed to run through the semaphore operation. So under Night Probe, here's the state here. If I now change this to hold, you'll notice that the data that are displayed here have ceased or paused because in the night view, because I now have placed it in hold, I no longer perform this semaphore operation to trigger the execution of the threads. So the threads eventually are not running because of this. So let's go ahead and let it run. I mean, we're still running. I mean, but the threads are not active because of that. Let's go back to run, and now you can see that these, in fact, have continued. Now, in addition to looking at data, there's a number of ways you can look at data. You can record this the data. The Night Probe is not really a data recording application, but you can record some information with it, along with timestamps. And it can actually be fed into the Night trace utility that we can talk about at another time. But with the Night Probe, I'm going to just to show you how you can data. I'm going to mark this one. I'm not going to mark it for recording. I'm just going to mark it for these two. I'm going to show you how you can actually visualize this a little bit. So I've marked both for the sine thread and for the cosine thread to for visualization. So I'm now going to go out here and add a page, and I'm going to view a graph, and I'm going to select these two and go to update, and we let this run a little bit, and we'll see here shortly that the sine and cosine waveforms will quickly appear. Again, for during your development phase and visualization, this may be something that would be useful to look at to see if the data that are being collected or being generated by your application appears to be reasonable to the naked eye. There are other ways of looking at data as well that may be of interest to you. And in this case, we'll take a look at another way to do this, is to look at in what's known as a spreadsheet. However, I will say that the spreadsheet viewer that it's referred to on a Night Probe is not, in fact, a real spreadsheet. The spreadsheet viewer is more of a tabular display. So in this case, I have these two selected, and let's go ahead and set those for automatic sampling. So here we have the two for the sine and the cosine here being displayed. But one thing about this particular display purpose or display method with Night Probe is that you can put thresholds on these cells. So you know, when you're acquiring process data or generating data from algorithms, you may have variables that may be outside the normal range, and you want to perhaps quickly be able to identify that. So I'm going to go in here on this one and say I'm going to set the thresholds for this particular cell, and so if the let's see, going to color this one as red. And new, and if it's 0, it's going to be green. So in this case, you can see now here at this cell, and that if the value is negative, it's going to be, it's displayed in with a red background, and as soon as it goes positive, it's going to be shown in a the other color. But you could set, in process control, you have high, low, high, high, and low, low, and so forth. So you could have a number of thresholds in here that you could red, yellow, green, or whatever.
A question, Michael.
Yes.
So just simple question, probably. So is there a way to group probes, right? So if we have distributed system, and we wanted to, put probes on different parts of the system, but group them by subsystem, is that possible?
I think can you explain that a little bit more, what you mean by subsystem?
Sure. So we have, let's say, an embedded board 1 and then a separate embedded board 2 inside the vehicle, and we want to, probe, do some testing or collect some probe, let's say, some parts of the code and the behavior of embedded board 1 and embedded board 2. Mm-hmm. Can we, and this is happening all together, but we want to group the probes, embedded system 1 and embedded system 2 separately. Is that possible?
Well, sort of, I would say. You can run multiple copies of these tools. So, for example, I could start up Night Probe and target it to one particular executable on one board, and start up another instance of Night Probe, and it would be running on the against the other one. You would have separate displays here. So, I mean, I don't have anything to really show you that here, but I mean, I could start up a second instance of Night Probe here. It's also being attached to the same same process, but this could be a different process altogether. So you could be looking at, in this case, it's the same one I'm attaching to, but yes, this could be running on one board, and this could be running on a different board altogether.
Okay. Yep, that works too.
Okay, good.
Yeah. Thanks.
You're welcome. So that's kind of a quick review of what the Night Probe utility can do for you. As far as, remember, it has nothing to do with the logic of the program. It allows you to look at memory that has been declared global or static to the process, because these are fixed address locations in the executable. And then finally, really the pinnacle of all the Nightstar tools is Night Trace. And so let's take a look at what we have. I'm going to actually run a few traces here with Night Trace. First of all, let's start it up on the system. I'll minimize this, do ntrace. But in this case, I'm going to start up the Night Trace GUI on my local laptop. Whoops, I meant to minimize that. Let's bring this. And this is the control panel or control center for Night Trace, the GUI interface. Now, a lot of this stuff can be done at the command line. So you can put a lot of these things that I'm doing here in shell scripts and run it. But in this case, I'm running it with the GUI. And when you start up Night Trace, by default, it comes up with a default kernel trace daemon. But in this case, that would be attempting to trace my local computer. But in this case, I want to trace this other computer remotely. And let's see. And we're just going to do a really generic trace here. And just so I'm going to launch the daemon. That caused it to be launched on the remote computer. It's now collecting trace data. The trace data is actually being streamed back to my local computer, my laptop, and for display purposes. Now, it could be recorded on the remote computer in the file system for postmortem analysis, as I discussed earlier. But so in 12 seconds, I collected about 347,000 trace events on the remote computer. And what I have here on the timeline is a visualization of what is occurring on that other machine in the other room. Now, this time when I'm running it, we're just looking at stuff. You know, you can't, you know, the old adage, you can't control the weather if you can't predict it. Well, that is also true with debugging. If you cannot predict what a program is going to do, how are you going to debug it? In this case, we're only looking at what's going on in the system itself. And so what we see here on the screen is I have CPU 0, CPU 1, CPU 2, CPU 3. This is CPU cores 0, 1, 2, and 3 on this remote computer. And for each of the CPU cores, I have a number of timelines running across here. And what you see in red is for interrupts. The next line down is for page or for exceptions. The next line down is for system calls. The next line down is for processes. And then finally, the trace events themselves. Now, on this screen, if I zoom out completely, what I'm looking at is 350,000 trace events being compressed into the screen. And so I really need to focus in a little bit on what's going on. So I'm going to just select a sliver of this and zoom in here. And so now I am looking at roughly from 6.054 seconds to 6.120 seconds. So it's what? A few, 50 milliseconds or so, something like that. And these, what we see here now are where, again, this is a lot like an oscilloscope. So I'm going to zoom in on just this right here. And so this is what's executing. This is what's executing on CPU core 3 at this time. And so we see an APIC timer interrupt occurring here. The interrupt exits here. This process gets switched in here. It's calling a system call called nanosleep. And the app happens to be that app program that we're running under Night View. And then app down here then makes a system call back to semaphore operation. And then after that, it gets switched into another thread from the app program. And then back to another thread. And then another thread, each one of them being distinguished by different colors. So the point is, you can see in very fine granularity what is executing on CPU cores across the entire system. And this is all for timing analysis. Now, let's see. Now, the graphical representation that we have here is generated by the GUI tool from the trace events that were collected by the night trace kernel daemon. The upper half of this particular screen are the actual trace events themselves in textual format. And we can see that up here, that we have trace event 0, and scroll down to the bottom, there's the last trace event at 347,000. So we have all the trace events that are occurring on that particular system, which CPU that trace event occurred on, what the event is. This is a system called enter. It was generated by the process nighttune. It was the thread. And then here is the timestamp. And what we use for nighttune is the timestamp counter that generates, that runs at the rate of the oscillator, so we get sub-microsecond timestamping. I'm running out of the hour that we set aside. I'd like to, if I could continue for a few more minutes, I'd like to, if that's, if both of you have a few more minutes to spare.
I'm okay.
Okay.
Yeah, no problem for me.
Great. Okay, so now analyzing this trace data by eye is not necessarily very productive, because you could have millions of trace events and you're trying to find out outliers, typically. Why did a process took too long to run, or why did it complete too soon, or something? So built within the nighttrace utility, we have something known as profiles. And a profile is nothing more than a specific search condition. So I'm going to use a profile here, and in this case, I'm going to find the state. And let's see, I'm going to look for, let's see, with night view in the context, the main thread was 529018 is the thread that was running. And what we're going to do with nighttrace is to find where that process was switched in and when it was switched out. So we're going to do a schedule switch and a schedule switch. Oops, need to learn to type a little bit better. And in this case, I'm going to say arg1 is equal to 529018, and arg2 is 0, and then arg2 equal to 529018. And arg1 is equal to 0. So this happens to be the way that nighttrace collects trace data. A schedule switch event, that's one of the kernel trace events, but it also passes arguments along with the schedule switch from trace event. And arguments that are passed, argument 1 would be the process being switched in, and argument 2 is the process being switched out. So I'm looking for a state condition where I'm going from idle to this particular PID, and then I'm going to be, then where I'm switching out is where that's going back to idle. So I'm going to summarize those events. And I just encountered an issue with the latest release of nighttrace. I apologize. Nighttrace does not have, we've gone from a 16-bit PID to a 22-bit PID, and nighttrace doesn't support 22-bit PIDs right now. So, so I'm not sure what to tell you. Okay, so I'm going to skip that for the moment and go back to one more thing. And I'm going to close this trace data here. I'm going to close this trace data that I previously collected. I'm now going to tell nighttrace that I only want to collect trace data this time from CPU core 3. This is where the application app is running, only on CPU core 3. But this time I want to tell, I also want to collect user tracing. And on Mini X, and it's set up to collect that from the user application. But the user application isn't set up to generate any trace events. So I'm going to go into night view, and at line 106 here, I'm going to generate a trace event here of 1. And at line 07, I'm going to also generate a trace event. It's going to be a trace event 2. So essentially what I'm doing here is demarcating how long I go into this function called work. So if I know when trace event 1 occurs just before I call the work function, and trace event 2 occurs right after returning from the work function, I now can measure the duration of the work function. So those trace events have been patched dynamically into the running application. So now over here with nighttrace, I can now select both of the daemons, launch them, resume them, let them log some trace data. Let's give it a few seconds to do that. Halt the daemons, and now I have trace data, kernel trace data of 144,000 trace events over 18 seconds, and I've got some user daemon data as well. So if we go to the kernel trace line now and look in here, I'm going to zoom into a little area here and zoom into another little area here. And one final zoom. So this is trace event 1. Now remember, this is occurring in the main thread. So that's trace event 1 is before the process called the work function, and trace event 2 is after the work function returned. Now, remember, the kernel tracing is looking down on the execution of processes and threads across the system. So the kernel knows when interrupts occur and when system calls occur and when processes get switched in and they get switched out. But between the time the process exits the system call here and the time it enters the next system call, the kernel only knows that the process compute bound. So if you're actually trying to determine what is actually occurring within the process, you can then use user trace events to look in finer detail of what the process is doing between trace event 1 and trace event 2. Now, that is all somewhat interesting, but we can also find out during this particular trace, where did it take the longest for this to occur during the trace. So I'm going to go back to profiles and actually create another one, and it's going to be in this case it's going to be trace event 1 and trace event 2 and all. Apply. One and two, I should have. And summarize it. So now the utility scans through the entire trace file, looking for trace event 1 followed by a trace event 2 and measures that time between there and then creates a summary for me. And that's what this particular page is. So here I can sort on here. This is where it took the least amount of time in the trace file. So this is between trace event 1 and 2 was the least duration. And I could go to where it was the longest duration. So this is kind of the power that you have with nitrace for doing these a detailed analysis. Now there's a lot more things about nitrace you can do than what I've shown you here, but these are some of the things that are done. So I run a few minutes over, but I hope this has been somewhat enlightening for you. And if there aren't, open for questions. And
Michael, I think really appreciate what you did. I'll give a quick summary. You guys, from my point of view, here are what I think are the highlights. So Night View, the debugger, what I think is really cool about it is that it supports hot patching live of your program without having to recompile. So if you can imagine, you can do your what if scenarios and just type it in, hit the button, and see how the application changes. And it's completely designed to be non-intrusive. So that's why, you know, the whole focus is real-time, non-intrusive debugging with hot patching. So that's maybe one of the highlights of Night View. Night Tune is really set up to give the customer a graphical interface for new people to be able to do easily shield the system and then optimize the performance of the system running the threads that are important to you, perhaps on the shielded cores. And then you can vector interrupts easily to a particular core as well, if an interrupt is important to you. So Night Tune is that, you know, you can do it all via the command line. You can do it via scripts, but Tune just gives you a graphical interface to make it easy for the customer for the first time. I would say Night Probe, you know, it's data recording, data monitoring, but you can peek and poke into the address space of a running application and modify variables and see how the application behaves. And it allows you to display and visualize live data and variables while the program is running. And I think that's really cool. And then Night Trace, I summarize it this way. It's a window into the computer that you don't have today. It lets you look at what's happening on every core, and it gives you the ability to look at the interaction between the operating system and your application on a nanosecond timeline with no special hardware. In addition, Michael demonstrated that you can put user trace points in. So when it comes down to it, and you think there's a problem in a certain part of your code, you can basically put a trace point before and after a subroutine and then display how long it took for that to occur. And then the thing will do a search and summary and take you to where it happened. And then you can look to see what the interactions were to determine really why a problem occurred. So we believe these tools really help somebody who's doing real-time programming, and especially, for example, 2 weeks before you have to deliver the product to the customer and there's a glitch. What do you do if there's a timing glitch? And you know, with other solutions, you're hooking oscilloscopes to the backplane of the computer trying to figure it out. With our solution, you're going to fire up Night Trace and you're going to see what's happening and you're going to visualize what's occurring on that computer. So tremendous time savings tool, and it is truly a window into the computer that we don't think you have today with any other product. So that's my summary of what these tools do for you, and you know, we're very excited about potentially working with you guys. So I know we're over the time, but I'll end there, and we can continue the conversation, you know, at your pace, or you know, whatever you guys want to do next.
That's thanks, Bill. That was a great summary. Michael, thank you again for the presentation. At least for me, it was very enlightening for sure. I think this is really cool stuff. And you answered some of the questions in your summary as well. In general, so the tools, not just Night View, but all the tools here are not intrusive, right? They don't impact the performance while the tool is running.
It's very, very minimal impact.
Okay. Yeah, the reason I ask is obviously it doesn't contribute to the problem at hand that is being debugged or,
Right.
based on.
Yeah, something, if you're looking for memory leaks, then the debugger has to step in and help you out.
Sure.
But for running real-time stuff, yeah, the tools essentially are very light touch on the performance of the system at all. Of course, if you're doing collecting trace data, it requires the kernel daemon to run, so you have to have CPU resources available to collect the trace data. If you're running at 99% utilization on your machine and you need to collect trace data, then you're going to have a difficult time.
Sure.
You have to have spare resources. But yeah, they're very, very light touch on the actual overall performance of the system.
I have another question. So in the night trace, as it looks at all this data it's collecting, does it have any more advanced intelligence built in where it can detect anomaly or abnormal behavior or anything like that?
Yeah, it does. There's the ability for that. Let's say you have something that occurs once every 27 hours, a bump in the road. And you know what it is, but you don't know exactly when it's going to happen. There's an API for night trace that you can develop a user application that will collect trace data and analyze it on the fly. So you could have the night trace kernel daemon collecting some specific trace data for you and then streaming it to another piece of code that's looking for this anomaly. And while nothing is occurring, this piece of code would be collecting maybe the 5,000 trace events leading up to it, and maybe 1,000 trace events after that point. And then when the anomaly occurs, then the user application could then save that save that away as a trace data. Then you can go back and look at it. So yeah, there's a lot of things that can be done with the utility to look for very rare instances or very rare events.
That's pretty neat. Thank you, Michael.
You're welcome.
Those are my questions for now. Over.
Okay. All right, you guys. Well, we appreciate you giving us the opportunity to show this stuff to you today. And, just let us know, what the next step is, and we'll do everything we can to support your requirements. So we're excited about potentially working with you guys.
Sounds good, Bill. Thank you.
Okay, y'all. Thank you very much.
All right. Thank you, guys. Have a good one.
Take care. Thanks, Michael. Bye-bye.
You bet. Bill, Bill, give me a call when you get free from your next meeting.
Okay, we'll do. Appreciate it, guys. Bye.
Goodbye, everybody.